Hey everyone, it's Justin again. In this lesson, we're going to be taking the exploration that you did in the previous lesson to solidify your understanding and go over the concepts together. Specifically, we're going to be discussing the area formula for regular polygons. By the end of this lesson, you will be able to use the area formula to find the area or segment lengths of regular polygons. First, we're going to review the properties of regular polygons. Next, we'll discuss the regular polygon area formula. And finally, we will complete 3 example problems. Let's take a moment to review some of the properties of regular polygons that will be important for finding their area. Regular polygons are polygons that have all sides congruent. They can have any number of sides, as long as it's at least 3, so they can form a closed figure. And since there are many possible numbers of sides for a regular polygon, we use the variable n to represent the number of sides of any particular polygon. For example, this regular polygon on screen now has 6 sides. Do you remember the name for a 6-sided polygon? This is a hexagon, and for hexagons, n equals 6. A regular polygon with n sides can also be broken into n congruent triangles by drawing in segments from each vertex to the center of the polygon. So this hexagon forms 6 congruent triangles. This regular pentagon with 5 congruent sides can be broken into 5 congruent triangles by drawing segments from the vertices to the center. And this regular heptagon with 7 congruent sides can be broken into 7 congruent triangles by drawing segments from its vertices to the center. These triangles are going to come in handy when it comes to finding the area of the whole regular polygon. But there's one more thing that we need. The apothem is the perpendicular distance from the center of a regular polygon to its side. Because of the symmetry of regular polygons, this segment is congruent no matter which side of the polygon it touches. Any of these apothems would all be identical. When we look at any one of these triangles, the side of the regular polygon is the base, and the apothem is its height, since they're perpendicular. And now we can find their area. To find the area of a triangle, we calculate 1/2 base times height. For these triangles, the base is the side length of the regular polygon. We'll call that S. The height is the apothem, and we'll call that lowercase a. So each of these triangles has an area of 1/2 SA. And if I put all of these triangles together, they make the total area of the entire regular polygon. In this hexagon, there are 6 of these triangles. So to find the area of the whole hexagon, we can calculate 6 times the area of one triangle to get the total area. Except this formula here only works for regular hexagons, since their 6 vertices create 6 congruent triangles. How would this calculation be different for a regular heptagon, or a regular octagon, or even a regular 20gon? Oh, that's right. We can say that any regular polygon has n sides and separates into n triangles. So we can take that triangle formula and just multiply it by n. Now this formula works to find the area of any regular polygon. There's one more thing I want to point out here. If we multiply the side length times the number of sides, that gives us the entire perimeter of the polygon. Another way you can see this formula written is as 1/2 perimeter apothem, with capital P representing the perimeter. Both of these formulas mean the exact same thing. So if one of these makes more sense to your way of thinking, that's totally okay. You can use them interchangeably. Keep in mind, these formulas only work for regular polygons, so make sure you have all congruent sides before you try to use it. Now that we have some formulas, let's put them to use in some examples. Our first example problem says to find the area of the octagon below with an apothem length of 8.45 meters. We also have a picture with one of the side lengths given as 7 meters. Here are our two equivalent area formulas for regular polygons. Before we start solving, let's double check. These formulas only work for regular polygons. Is this a regular octagon? Yes, and we know this is a regular octagon because these marks tell us that all 8 of these sides are congruent. Okay, phew, now we can proceed. Which version of our formula do you think will be easier to use for this problem? The one involving side length or the one involving perimeter? Since we were given the side length, it will probably be easiest to use the side length formula. To use this formula, we need to identify the side length, apothem length, and the number of sides. Pause the video here and identify these values in the problem. Did you find that the side length is 7, the apothem is 8.45, and the number of sides is 8? Nice job! We were given S and A, and we can get 8 for n by either counting the sides in the shape or remembering that octagon means 8-sided polygon. Now all that's left to do is to substitute and evaluate. If you haven't already, pause the video here to finish this problem off. After substituting, the equation should look like this. This expression is what I'm going to put into my calculator, which gives me back 236.6. Since our lengths were measured in meters, the area should be measured in meters squared. And there's our final answer. Let's move on to the next example. This problem says to find the area of the pentagon given that its perimeter is 125 millimeters. We also have a picture where the perpendicular distance between the center and one side is shown as 14 millimeters. Here are the two equivalent area formulas for regular polygons. But before we start solving, let's double check. These formulas only work for regular polygons. Is this a regular pentagon? Uh-oh, no it is not. These marks show that there are at least 2 different side lengths in this pentagon. So this pentagon is not regular. We can't find the area of this pentagon since it's not regular, at least not with this information. This is why it's so important to make sure your polygon is regular before proceeding. Since we can't find the area here, let's move on to the last example problem. The final problem says to find the area of the regular hexagon given that its perimeter is 132 inches. We also have a picture where the perpendicular distance between the center and one side is shown to be 19.05 inches. Here are the two equivalent area formulas for regular polygons. Did you remember to check that this is a regular hexagon so that we can use one of these formulas? Yes, the problem text tells us that it's a regular hexagon, so we can proceed. Which formula do you think will be easier to use for this problem? The one involving side length or the one involving the perimeter? Since we were given a perimeter, the perimeter formula makes more sense this time. Pause the video here and try to finish off the problem independently. Did you identify that 132 is P and 19.05 is A? From here, you should have substituted into your formula and entered this expression into your calculator, which will give you an answer of 1,257.3. Since our lengths were given in inches, our area is measured in inches squared. And now that it's properly labeled, this is our final answer. To find the area of a regular polygon, you can use either of these formulas. They're equivalent, but this form is more convenient when you're given a side length of your polygon, and this form is more convenient when you're given the entire perimeter. Don't forget, always double check that your polygon is regular before trying to find its area, since these formulas only work for regular polygons. Good luck on your practice, and I'll see you next time.